So Callum is from Cornwall. He's very modest actually, but he's super talented. He does lots of things, not just functional programming, but he loves working with operating systems and attacking them from all sorts of directions. He writes compilers and he runs a proper operating system. Which, so let's welcome Callum. Thank you very much.
Good. Functional programming. It's all about functions, but not the kind of functions you have in C or like Java or anything like that. Mouse. My examples through this are almost entirely in Haskell. There are a few other languages, but there's like a huge number of functional languages available. There's like, you've probably heard of Lisp. There's loads of different types of Lisp, but you can also do functional programming in like probably the languages you're using already. So like Python, C++, Java, C#, all of these have support for functional programming. So you can try out these ideas in your favorite language. So the big things with functional programming is you treat functions as values, just like you treat integers or booleans or anything like that. And the functions are you just think of them as mappings between things. They are like just immutable relationships between different sets of values. They're not sequences of instructions like you have in any other kind of normal language. So it's purely this kind of relational aspect of it that you kind of focus on. So they're a lot more like functions from mathematics, where you might have f of x is equal to x squared or something like that. That is to say, they can't do something like print something to the console just directly, or delete all of the files on your disk or something like that. And the referential transparency thing I've got here, this is just saying about how anytime you give it the same input, it's always going to have the same output. So that's all referential transparency means. It's a bit of a weird term for it. It sounds very kind of fancy, but it's pretty simple. And then another thing is the data you have in your program, that's also immutable as well as your functions. So like you can't, for example, assign 4 to something and then modify that to be 6. You can't do x equals 4, x equals 6, because that would imply 6 equals 4, which is false. And this seems like it would be a limitation, but actually the fact that you can count on values staying the same, it means that you avoid a whole slew of problems that other languages and other paradigms run into. So you don't ever have to worry about, for example, data races realistically, because there's no other thread that's going to come and modify some state that that's going to cause problems for you. The big thing in programming, I would say, is managing complexity, right? Like, it's all that we really spend our time doing as programmers is we spend time thinking about the problems and how to solve them, but realistically, a big part of it is just dealing with the fact that we have this really complex system and we need to be able to change what it does and guarantee that it does certain things, guarantee it doesn't do other things. And so we create abstractions on top of that to simplify it down and to make it so that our puny brains can deal with it. But obviously, that counts on you having good abstractions. If you have bad abstractions, then they kind of just get in the way, right? Like, you're like, oh, so this subsystem of behavior is wrapped by this thing, which apparently is supposed to hide away all of the details, but I'm just having to read through how it's implemented anyway, so what's the point? And it's huge pain in the ass, and that is partially caused by the fact you have this mutable state, right? Because you have to concern yourself with with what changes is this function making under the hood that might collide with some other changes a function is making. Obviously you can avoid, everyone knows to avoid things like global variables and things like that, but more subtly, like within the confines of a particular object, for example, the fact that a particular method might mutate something within that object means that, for example, you can't invoke that method in parallel. And unless you have good documentation saying that that is the case, someone might think, oh, this should be fine, right? And you'll end up with problems. Yeah, data races, illegal state exceptions, terrible, terrible pain. And that's because there are implicit dependencies just all over your code, right? Like, you have a particular line of code and it's just making this huge pile of implicit dependencies, implicit assumptions about the state of the system and what it assumes has happened prior to it. And it working properly is entirely dependent upon that state being set up properly. And if someone else makes some change further up the program, that can mess that up, and you can have unexpected behavior. And it's all because of just these hidden assumptions about the state of things. So if you get rid of that mutable state, the only way that one bit of a program can influence another is by returning a value and then that value getting passed into the function. You make all of those assumptions completely explicit in your code because you have the function and you have the things it depends on being passed into it directly. You can just see it like right there, and you don't need to like read thousands of lines of code to be sure, oh, I can change this thing and it won't create some terrible catastrophe. And of course, abstraction isn't a new thing. Mathematicians, for example, have been dealing with the problem of how to simplify complex systems for hundreds of years, way longer than computers have existed. So we should copy them. And the idea of a function in the functional programming sense, a pure function, is basically stolen from mathematicians, and it's a very good abstraction because all you have to care about is how it relates the input to the output. It can do it in whatever way you want, as long as it's not mutating state. You never have to care about anything else except what it outputs given an input. There's another kind of abstraction as well as functions that you have in mathematics, which is the concept of an algebra. So that's a particular set of things which you can manipulate in certain ways. You have these operations you can do to these objects, and you have a rigid in a mathematical algebra. You have a particular set of laws which govern those rules for a particular system, and there are names given to these particular sets of laws. So monoids, groups, and functors I've put up as an example here. But those are just sets. Like, for example, you have numbers, and you can do like addition, subtraction, multiplication, etc. And so you have like one algebra is the algebra of a field, which just abstracts over something where you can do addition, multiplication, subtraction, and those sorts of things, and they have certain structures to them. And likewise, well, what that enables in mathematics is you can prove something about groups in general or fields in general. If you are only ever using these operations you do to the elements, that means that if anyone then invents another thing which happens to be a group, they get the theorem that you've proven for free. It's just automatically true of their system, even if you never talk to them and they never talk to you. You just know it to be true because you have this set of axioms. In Haskell in particular has great things in the type system for this kind of axiomatized system. Yeah. So let's just see. How am I gonna? Yeah. So see here. This is a declaration. Just up at the top. This is a declaration of a thing called a type class in Haskell. So a type class is similar to these ideas of algebras. So what I'm saying is I'm going to declare a thing called streamable. Oh, incidentally, class in Haskell, don't think it's the same as class in the object-oriented sense. It's kind of a confusing name for that reason. But yeah, it's kind of a separate thing. You can sort of use them for similar ideas, but...
is it a bit like a protocol?
It's kind of like I think the closest thing in object-oriented programming is an interface, yeah, or a protocol kind of thing. Yeah, but it's essentially what this is saying is I'm going to declare a class streamable, and a type is going to be streamable if there are these functions that I can do to it. So if I can get the next thing in the stream, if I can construct a stream if that's getting something and sticking it on the end. If I can tell if a stream is done, or if I have an empty stream. So the type annotations here, I'll use this actually. The type annotations here. This is saying T is our streamable type, and it's actually like a wrapper around another type. So it could be like a list, or it could be whatever really. If I have, say I have a list of integers, it's going to give me, next is going to give me a pair of a particular integer, and then it's going to give me the list of integers. So this is going to be like the first thing in the list and the rest of the list, for example. And then cons is going to take a particular element, take a stream, and going to give us a new stream with that on the end. Done is going to take a stream and tell us whether it's finished, and empty is just going to be a particular stream value. So then here I'm defining a function here, double stream, which says if I have a number type, a numerical type, and I have a streamable t, and I have a t of a, so that's like a streamable collection of numbers, then I'm defining this double stream to be a function taking one of these collections and returning another one. And all I'm going to do is, if it's done, then I'm going to return the empty stream. Otherwise, I'm going to get the first thing in the stream and the rest of the stream, and I'm going to construct a new stream where I double that first thing and I stick it on the end of wherever I get when I double the rest of the stream. So this is kind of a recursive definition, and in general you're going to find a lot of recursion in functional programming. Definitely helps to be used to recursive definitions. Yeah. Oh, by the way, if anyone has any questions, feel free to ask, because.
What's the dollar do?
Huh?
What's the dollar operating?
Oh, the dollar. So the dollar here is basically, it's just normal function application, but the difference is that it's lower precedence. So I could here just surround double stream x's in parentheses. The dollar just lets me not do that, basically.
One of the most confusing things about Haskell.
It is. I don't know. I don't quite know why, but Haskell programmers really hate parentheses. I mean, myself included, but I couldn't tell you why. Yeah. Yeah.
It's like
No more parentheses, please. Yeah. So then, so this double stream thing is defined for any possible, because I've only used these things. If I can just if I invent a type and I define it to be streamable and provide implementations for these functions, then automatically I can use this double stream. And that's what I'm doing here. I'm declaring the list this is like open bracket, close bracket. I'm declaring the list to be streamable, and here I'm providing implementations for those functions. Yeah, so then I can just, if I just load this up, I can, for example, do double stream. Oh, this is really. Double stream 1, 2, 3, 4, and that will do that. But then likewise, I could use any other type here as long as I provide these for it. Going back to it being a bit like interfaces, I think the main difference I would say with interfaces and classes actually is that you don't have to declare it to be, you don't have to declare a type to be of a particular class, of a particular type class, in the same place where you define the type. So like interfaces, certainly in the languages I've used, you kind of have to, as you're defining the type, you have to say, oh, and it implements this interface. Whereas that isn't the case at all for type classes. Some other library could define a type, and then some other library could define a type class, and then you can say, oh, this type is of this type class in your own code, which is super useful. Yeah, and there are a bunch of these type classes that are really useful baked into Haskell. So another example down here is the foldable type class. So a fold, I should probably explain what a fold is.
I was wondering for my colleagues that came on, if you wouldn't mind explaining what a type is for someone that's not used to types.
Oh yeah, a type is basically it's a set of values, so a set of possible values. So like example of a very simple type is like a Boolean type, so that's either true or false. But then you also have other types like strings, which are used to represent bits of text, and that set of objects contains an infinite number of things. But they're used to, it's like different kinds of data, like integers, strings, booleans, yeah, rational numbers, that kind of thing. Yeah. But yeah, so a fold is basically, if you imagine it's going to, I'll just give an example. So if I do a fold here, the L stands for left, incidentally, but don't worry about that for now. So I'm going to pass in a function to it, and the way we're going to define a function here is with this this syntax where we have a backslash. Read this as a lambda, because this is called a lambda expression, what I'm about to type out here. And so x here is the argument of this function, and then arrow is going to indicate the thing that follows is what gets returned when x gets fed in. So if we do, and I'm going to need another argument here. If we do ac plus x, so that's going to take two things, and it's going to return the sum of them. If we do a fold, starting from 0 over the list 1, 2, 3, what this particular thing is going to do is add these up. And the way it's going to do it is it's going to have a particular value that it's kind of building up. It's going to have like an accumulating value, which I've kind of called ac here. This is our initial value for that. So we're going to start at 0. And then for every element in this list, we're going to pass the current value of the accumulator and the element we're looking at into this function given in here. So it's going to start out with ac of 0, then it's going to add 1 to 0, get a new value of 1, then it's going to recursively go through and get 2, add 2 to 1, etc. And so we'll get 6. Yeah, so that's the idea of a fold. And you can kind of tell here, this needn't really be a list. All you need to be able to do is kind of iterate along it in this particular way. And so in Haskell, in order to use fold on a particular thing, it doesn't have to be a list. It only has to be part of the foldable type class. And so here, I've got this other type here, which is a tree. And I've just said, so if I have a tree of containing values of type A, that tree is either going to be empty, or it's going to be like a node with a certain value, and then, oh, this is a binary tree, by the way. It's going to have child trees, and it's going to have 2 of them. So it's going to have a tree on the left and a tree on the right. And then I've defined an instance of foldable here for this tree type. And you only have to implement this one function for foldable, which is quite nice. There's actually a whole bunch of different functions you can implement. But one way to define a foldable instance is to use fold map. And then I have a particular tree down here, which is just, contains some values. And because I've defined this foldable instance, that means that I can do things like take the sum of that tree, or I can do the length of it, and things like that. And there's a whole slew of functions which all they need is for a data structure to be foldable, you get them for free. So this is like some of the things you can get. You can get length. You can check if something's in it. You can do a fold L. You can do fold R, which is the same but going from right to left. You can convert it to a list. All sorts of stuff. So that's an example of the kind of taking inspiration from the mathematical way of abstracting things by means of defining the operations you can do, rather than defining a particular any particulars about I don't know, data structures or anything. All you say is there exists this function which has this type. It's very, very kind of unspecific, I guess. So another thing you kind of that gets easier with functional languages is testing. So a big part of testing is making sure you have everything set up that your system's going to be using. Whether that's like a file system, obviously file systems are slow, so often people mock them out. All of that stuff, it's kind of a bit of a headache. And like I said, dependency injection is quite a pain. It's fine, but it's a bit of a pain. In comparison, because you're only ever dealing with pure functions that just map an input to an output, you can literally just make a big table of inputs and expected outputs, and that's fine. Like that does the job. You can also do a thing called property-based testing, which I don't know if anyone's heard of, where you define kind of in an abstract way, when like you might say, when I pass in a integer that divides by 2, it says, I don't know, it returns 7 or something, I don't know, whatever. But you're defining properties of the system, and then the property testing framework basically generates a bunch of random data that fulfills those requirements, feeds it through, and makes sure that the requirement is met. So testing is a lot easier for functional code, because because it's all just mapping inputs to outputs. Yeah. Also, yeah, formal verification, staying on the whole like making sure your programs are correct kind of thing. Formally verifying code with things like C or Java, it's a huge pain in the ass, right? To actually specify and model your software in a rigorous enough way that you can mathematically prove things about it. Like, that's a lot of work. It's very expensive. There's lots of room for errors to sneak in. In comparison, a language like Haskell has the advantage of it's already got strictly defined, very formally defined semantics to it. So converting your code into a mathematical model of your code is something the compiler can do for you in a lot of cases. You can literally, there exist extensions to the Haskell compiler to generate code in a language called Coq, which is a proof checking framework. And you can just literally take your Haskell code, convert it directly, and then prove things about it with very few intermediate steps and very few manual steps. So it's much cheaper, much easier to do, and you're much less likely to mess it up.
Can I ask a question, just going back a slide around testing?
Oh, yeah.
So with a normal language like, I don't know, Python or C or Java, you're often testing inputs against what you think the outputs should be.
Yeah.
And clearly that's a big space, and it's an exhausting task making sure you've got the right coverage and the right kinds of coverage. Are you saying that with functional languages, your testing is reduced to matching input type and output type? Because as long as those match, you've automatically confirmed it for, you know.
Not quite. What I'm really saying is, like, if you have some part of your system written in an imperative language, the behavior of that doesn't exist in isolation from the rest of the system, because well, typically it just typically doesn't. And so it's you have to do things like mock out the file system, mock out the I/O of various kinds, and therefore you can accidentally introduce problems into your testing by, for example, like your mock's behavior doesn't quite match up to the behavior of the real thing, other than in terms of speed.
So when you're testing a complicated functional program, what is it that you're testing?
You can just test because the functions are pure and exist in isolation from the rest of the system. Yeah, you don't really have to mock in the same way. You can just replace one thing with another in much the same way. Like, I don't know.
So you're testing small units, and you're saying because they're pure, the composition of those small units is going to be fine.
You would also want to test the composition of them, yeah. But I guess what I mean is, like, in like Haskell, for example, the I/O and all of this stuff is already abstracted away because the model you're dealing with is pure. So all of the sorts of things you might want to remove from your system while you're testing it are kind of already removed for you in a sensible way by Haskell itself. And so then you just have to say, oh, instead of doing I/O, I'm doing fake I/O, and it's kind of already done for you. Yeah, so I don't know if anyone's heard of monads, but like in Haskell, all of the I/O is done through the I/O monad, and you can literally just replace. You can write your code to work with any monad which fulfills certain things, and then you can just replace the I/O monad with a different one, and then magically all of the IO turns into mock IO without you having to do any kind of dependency injection or change your code whatsoever. Does that make sense?
Is it monad like a singleton?
No, monads are quite complicated. They're kind of like a context in which they're a context to a certain value.
They allow you to break the rules.
They don't really allow you to break the rules. They allow you to break the rules without looking, well, no, they allow you to not break the rules while it looking like you break the rules.
Right.
Yeah.
So they kind of hold global state, but
They don't,
not the way they were defended here.
they don't hold global state. They are kind of just a bit of extra information tagged onto to a particular value. So if you have, like for example, with the IO monad in Haskell, if you could have like an integer, but then if you're getting an integer from the user, that's not just going to be an integer, that's going to be an IO integer. And what that essentially means is that it's not really, it's got this extra context on it, which is basically a big buffer of IO events. And you can't separate the value from the context. You have to deal with it inside that IO context, so it doesn't really leak out anywhere. But then there are other ways that you can map operations over monadic values, and that lets you do things like you can double things and all sorts.
So it's a way of changing the outside world from the pure language.
The projector's gone to sleep.
So like in your testing, because functions are pure, they can't have side effects outside of that function. So whereas you might run something that prints the date in an imperative language, in a functional language, the clock would have to be passed in as a parameter.
Exactly, yeah. So you just pass in a fake clock as a parameter.
So you'd be like, you could guarantee your tests will always pass, because if you put these inputs to this function, it should always return this output, which you can't get unless it's a pure function.
It has no internal state either.
Yeah.
You've got nothing that isn't visible.
Yeah. So yeah, formal verification. There's a really interesting new area in functional programming languages, which is dependent types. Has anyone heard of dependent types? Dependent types are really cool. Yeah, you can. In a dependent type system, it's kind of hinging off this fact that there's sort of an equivalence between types and theorems and programs and proofs, which is super interesting. But yeah, so you end up with incredibly descriptive types. So like, whereas normally you might have like a vector type and you can have a vector of integers, in a dependently typed system, the size of that vector might also be a parameter that you specify. So you can express a lot more about the behavior of your program through the type system and have it checked for you by the compiler, which is very nifty. Just
so
find
more specific types that you specify by almost like inheriting from
Yeah.
the type.
Well, so it's not quite inheritance. It's that the types themselves contain a field where you specify the length.
You can constrain types, value of types, as well as the
Yeah.
type.
Yeah, so here, this is now, it looks a lot like Haskell. It's not Haskell, don't be fooled. It's Idris, which, yeah, the main difference you'll notice is the colon and the double colon are swapped. This now means has type, this means stick something on a list. Yeah, so I've got this append thing here, and it's going to take a vector of n elements of type A and a vector of m elements of type A, and it's going to produce a vector of n plus m things, and I can actually say that in the type, right? Like normally that would be a thing you had to test and had to make sure yourself that you got correct. Obviously with this it's a very simple program, but the compiler will actually check this for us. So if, for example, here I say I'm gonna just like put x on twice, this will now actually give me a compile time error saying this type is no longer upheld, which is super cool. So you can essentially, if you have a descriptive enough type, then just the fact that your program type checks can be thought of as a proof of correctness, a formal proof of correctness. Another really cool aspect of dependent types is that because you're giving all of this additional information to the compiler, it can do a lot more stuff for you. So Idris specifically is a big part of what Idris is trying to do is make the whole programming kind of workflow much more back and forth between the compiler and the programmer. So I can actually tell the Idris compiler, fill in a blank thing for me, and it will do that. And then I'm just hitting key bindings here, by the way. Yeah, and then here I can say, okay, so I have this x's thing, but what are the possible cases? And then I can just tell it, split out those possible cases. And so it said, oh, well, either you've got an empty list or you've got something on the front of the list. And it'll just fill that in for me. And then I can do the same here. And it will say, oh, well, if I've got a vector of NA and it's empty, and I have a vector of NB, and that's also and n is 0 here. So therefore this must also be empty. Oh, I should probably explain what I'm actually trying to do here. Zip with is basically going to take a list of elements and it's going to feed them both into a function, and that's going to become an equivalent element in a new list. So it's kind of going to zip them together with this f function here. So like this could be integers and a vector of integers and a vector of strings, and it could be like, I don't know, making the character at that index uppercase or something. I don't know, that's just a strange thing, but yeah.
So with the dependent types, am I right in thinking you could create a type that was like a list of strings that had to have 3 elements in it?
Yeah.
And if it didn't, then it would warn you at compile time.
Yeah, exactly.
Time.
Yeah.
So that would be a whole slew of bugs gone.
Mm. Yeah, precisely. And then you're also free to, there are other types, like the vector in Idris is specifically like a sized list. If you have places where the size varies, you can also, there are also unsized lists. Likewise, you can also specify things like, you can specify properties of this n here, so you can like specify that n must be even, but that gets slightly more, I don't know, interesting, I guess. Yeah, so now I've got this one case here where we're zipping 2 empty lists together. You know, it's quite obvious I'm going to get an empty list. And I could just type that in myself. But I can also tell the compiler to search for a possible solution, and there it gets that it's an empty list. And likewise here, I'm like, okay, so I split out this case. Now I'm going to try and split out these cases. Again, because it knows that the length is the same, it knows if the first one isn't empty, the second one isn't empty. So when I case split on there, it will just put in y onto y's. And now here, I can again tell it search for a possible solution. and it actually just writes this out for me, which is exactly what you want it to do. Because realistically, I've got X, which is of type A, and I've got Y, which is of type B. I've got F, which takes something of A, something of B, and returns C. And I want to end up with a vector of C, so it makes sense to feed in X and Y to F and stick that on the front of a recursive call to zip with. And the compiler can just figure that out for you, which is super useful. Obviously, it's not going to figure out anything like really hard, but this is super useful just for like kind of plumbing code, if you know what I mean. It can often just generate a lot of stuff which is just laborious otherwise. It's very nice. Yeah. So that's dependent types. Yeah, and like I said, type checking is basically equivalent to formal verification if you have specific enough types, which you don't necessarily have to, but you can if you want. So yeah, another kind of big feature of Haskell specifically is lazy evaluation. Lazy evaluation, the essential idea is that rather than, if you have a particular computation, rather than running it immediately and getting the value, you're instead just going to wait and leave it in like a half evaluated state, or not even half, like just a not at all evaluated state. And you'll only actually compute the result once you come to need it. The advantage of that is that if you never do actually use the result, it will never get calculated, so you don't have to worry about it slowing anything down. And yeah?
Is that like when you have a function that returns multiple things, for example, and you only want to use one of those things?
Yeah. Exactly, yeah. In that case, that value that those values you're not using are just going to get thrown away. So they'll never get evaluated, and so you'll never have to deal with the runtime cost of those. And I have another example of lazy evaluation here. Another thing, so lazy evaluation lets you use infinite data structures, which is very cool. So here, there's a tiny bit of code, but this is actually defining all of the Fibonacci numbers. And it's doing it using laziness, because notice this is recursively referring to itself. And also scanl here, scanl is a lot like foldl. The only difference is it's, rather than producing a single value at the end, it's going to, for each step along the way, it's going to append the current value of the accumulator to a list. And it's just going to build this list up as it goes along. So what's going on here is we're starting out with the value 1, and then we're doing a scanl with the accumulator starting at 1. And so that's going to get that 1 off the front, it's going to add it to the 1, and then it's going to make 2, and so on and so on. And it's going to add, each time it's going to add the previous 2 to make the next one, which is exactly the definition of Fibonacci numbers. So
How do you use other than doing the Fibonacci series?
it does, yeah. I just really like this way of defining it, which is why I've used this particular example. I think it's really nice. Very short and kind of terse. Yeah. But no, laziness is absolutely, it's actually super useful all over the place.
I didn't mean laziness, I meant scanl.
Oh, scanl. Oh, right, yeah. Yeah, no, it does. I've definitely used it, but I can't think of an example off the top of my head. Yeah. Yeah. Oh. Okay. So yeah, if I just type fibs, it's an infinite list. So it's just gonna keep going forever which is, nice. But I can also do things like I can say take 5 fibs, and that's just gonna take 5 off the front of the list. And then because it's an infinite list, in a strictly evaluated language where it evaluates everything straight away, this wouldn't work, right? It would just fall over as soon as you try to define the infinite thing. But here it's just gonna only ever look at the first 5, so the rest aren't gonna get evaluated, and so they won't cause any problems. So we just get the first 5 Fibonacci numbers straight away.
Just out of interest, what happens if you tail the end of an infinite list?
Then you get another infinite list. Just with the first thing missing, yeah. So like I could do, I don't know, take 10 of tail of fibs, and then it's the same except we've just cut this extra one off the front there. Yeah. Any other questions about that?
Yeah, that last thing what you just did, that's...
Oh, yeah, so what this is doing, it's fibs, and then tail of fibs, and then take 10 of tail of fibs. The dollar here is right associative. It's going to be doing it from the right this way.
And the same as but first, isn't it? All first.
Yeah. Tail is. Oh yeah, tail is just.
Tail with like you said, with the last of the infinite series.
Oh no. Oh, the last item. Oh, I see.
Well, there is no
last, it will just never. It will not halt. It will just. It won't crash. It will just. Well, it will probably get killed by the operating system, but it'll just be an infinite loop. Yeah. Yeah. Oh, tail in Haskell means everything except the first element. So.
So it's like CDR in this.
Yeah.
If I remember it that long, then
Yeah, the car and Kuda, and Kadada and Kada and Kadadadada, all of the ridiculous names.
You know that last function you ran there?
This one?
Yeah, would you be able to run it again, but with parentheses instead of the dollars? So
Oh yeah,
so
sure.
you can see what it would look like in a different language.
Yeah, so it would be take 10 tail fibs, like that. Yeah. Right. Yeah, all right, so parallelism. Yeah. Parallelism is another big thing. I think probably one of the most compelling reasons, in my opinion, to use functional programming, as I've written here. Brains are bad at parallelism. Hardware is bad at not parallelism. Increasingly, it's becoming harder and harder for single-threaded execution to speed up, and so we're finding more and more multi-core systems, and it's becoming more and more important to exploit that parallelism that the hardware has available. But it's really hard to reason about loads of things going on at once. It's hard enough if you have like 4 things going on at once. If you have like 10,000 things going on at once, it just, brains can't do it. But compilers absolutely can, which is probably just as well, really. So if I load up my other example, is it 5? No. So I have here, I've got something written, 2 equivalent programs. They're going to compute the sum of the squares of a sequence. One's in Go and one's in Haskell. I'm not a Go programmer, by the way. This might be horrible Go code. I tried to make it as nice as I could. Yeah. But so here we're kind of using a channel of empty structs, kind of like a semaphore. So it's gonna, we're gonna spawn off a thread or a Go routine, sorry, or whatever the name for them is. That's gonna take a number. It's gonna compute the square of it and store it in a slice, and then it's going to squirt the empty struct into this channel. Then we've got a loop down here, which is going to add them up as it. It's going to wait till it receives that number, the number we're expecting, and then add all of them up. So that's going to be our. That's a kind of imperative version here. And you can see, like here, a lot of the complexity here is dealing with the parallelism. We're having to 80% of what we're doing here, if not more than 80%, is just faffing about, trying to make sure we don't that the different bits of code don't tread on each other's toes. In comparison, the exact same thing done in Haskell. All we're doing here is we've got this map function. That's just going to run a function across a whole list. So if we've got a list of values and a function that operates on those, it's just going to go through, make a new list, which each value in the list is the value in the input list with the function applied to it. So we've got that, and we're going to sum them. So without this being parallel, you just remove this bit. If you weren't doing it in parallel, you'd only remove this bit. That's the only thing that you have to add. And all that this is doing, this is just telling it that we want to evaluate these eagerly, essentially. As in, we're not going to leave them off, because, like I was saying, Haskell is lazy. So it's all well and good if you're like mapping, creating all of these square things in the list. Those could all be done in parallel, but they're only going to get executed. Those computations are only going to get run when you're going through the sum loop and you're actually using them. So it would actually just end up being sequential. By saying this using rddeepsec, we're basically saying that we want to evaluate each thing in this list now in its own parallel thread. And so here, because we know that this lambda isn't going to modify anything, it's just going to create a new value, then yeah, we don't have to do any of this messing around, trying to stop functions from messing each other over. Yeah, any questions about that? Cool.
So, sorry, I'm a bit slow on this. So the reason this works is, in terms of the actual memory that's in your computer, is because they're not going to overwrite each other, because each thread or line is actually separate memory that is being allocated.
Yeah, so each function each function it's never going to try and modify the same memory as another thread is trying to modify, because it's never going to modify any memory. It's only ever going to write to new fresh memory, or something that's semantically equivalent to that.
So with the imperative approach, again, I'm not an expert, with the imperative approach, some people like it because you can control how much memory gets used.
Yeah.
Isn't the challenge here, deliberately being devil's advocate, that actually your memory consumption can explode?
Absolutely, yeah. And I mean, like, memory usage is one of the things I would say that imperative languages very much have over functional languages. Yeah, if you have a problem where memory usage really matters and you need very predictable memory usage, absolutely do not use functional programming.
So this is
or certainly I wouldn't.
There was a serious point behind the question, which is I tried to learn Haskell, and I read a paragraph in there saying, in the old days, people were concerned about memory consumption of functional languages, but they're not so concerned anymore. And I don't understand the reason why that was the case.
So a big part of that is also compilers have got very clever now. So like you can do things like your compiler might say you've got like some data structure you're changing, and you want to change one thing in it. The way you would do that in an imperative language, you just mutate that thing, whereas in a functional language, you'd make a whole new one and with that thing changed, which obviously is very, if it's compiled naively, it's very, very inefficient with memory. But there are now mechanisms within most functional, well, certainly GHC, which is the most commonly used Haskell compiler, will try and notice when you do things like that, and it will, under the covers, just modify the thing. The advantage you get by not specifying that you are modifying it is that you're leaving it up to the compiler to make sure that that's correct, right? It only needs the code deciding when it's safe to mutate versus make a new copy only has to be in one place. You don't have to decide, oh, is it safe to mutate this thing every single time you're making something.
I think a lot of that was driven by cost as well. So computers used to be economically expensive to run, so they had to be really efficient, but now it's our time and cost.
Yeah, that's true as well. Yeah, so that's parallelism. And yeah, much the same kind of thing. Yeah, you kind of preempted what I was saying on that, actually. Yeah. So there's actually a whole bunch of other compiler optimizations. So you can memorize. The compiler can decide that it makes sense to memorize something, because of referential transparency, every single you can memorize every single function. It's always going to provide the same output for the same input. So you can just, if you're only going to have a finite set of inputs, then you can just tabulate the whole function and save a lot of processor time. Obviously, most of the time you have really huge input sets, so you wouldn't want to do that in practice. But the compiler can look at a particular function and it can decide it makes sense to memorize this, or it makes sense to inline it. You can also inline pretty much any function. And the fact that these functions don't have side effects means that inlining or memorizing them won't have any effect on the behavior of the function, because all that the behavior of the function is mapping the input to the output. It's not like if you had an imperative function which took a number, printed foo, and then returned double that number. If you memorize that and you use the lookup table instead, obviously it's not going to print foo anymore. So you have to be much more careful in imperative languages about this and this kind of stuff. And like I said, easy symmetric multi-core processing is another thing which can lead to Haskell and other functional languages actually being pretty fast. And yeah, also a lot of the time the thing that you're doing isn't actually CPU bound. The bottleneck in this situation isn't the processor, it's something like the disk or the network. And in those cases, the additional overhead you'll get for using something like Haskell is actually, it's still going to finish all of its execution before like a network request comes back anyway, so it doesn't actually make any difference. Especially with more and more SSDs and things like that around, a lot of certain types of SSDs can actually benefit from parallel access, I've heard. So that's pretty cool. And you're definitely not going to get that with naively written C, but you might get it with naively written Haskell. Brings me on to my next example, which is a Haskell clone of, do you know the Unix utility WC? It's basically a Haskell clone of that that is faster than the GNU implementation of WC, which is pretty cool. Where is it not? Yeah, so here I've got, I've just checked out their repo. I've just built this beforehand because you guys probably don't want to wait as the thing compiles, and just got the executable there. And if we time the execution of our normal WC on a big random file. This is like a 1.2 gigabyte file, and it's just filled with random ASCII. We'll see, we get about that much. You know, fine. If we run our Haskell one on it, oh yeah, this needs to take a additional thing here. This is when it's going to be much slower. Oh, there we go, faster. And if we run them both a few more times to account for things like disk caches and so on, you'll see it's consistently faster. So this one's getting around the 5 point something mark. 6 point something, and then this one, and this is written. This WC is written entirely in Haskell. It's also much less code than the GNU one. Yeah. So yeah, Haskell can be faster than C, but it probably won't be. Obviously.
What's the core mechanism that's making it faster?
The core mechanism that's making it faster is essentially the Unicode handling is one of the things that's making it faster, if I remember correctly. The Unicode, there's a really, the Unicode package that they're using is faster than I forget what IBM's thing is called. But IBM has like a library for Unicode, and that's what's used in the GNU.
So it's not parallelized, it's not chopping up the file and saying...
Oh, it is also parallelized, yeah. But because this is a disk-bound thing, that doesn't make as much of a difference, I wouldn't imagine. But it will make some difference, yeah.
Well, the user amount is actually closer to the GNU one. The root time is less.
Yeah.
Because that's the user one is the sum of all the cores at the end.
Yeah, the user one is quite a lot closer. Yeah. Yeah. So yeah, then with respect to data science, I think data science kind of naturally falls into a functional way of looking at things, because it's very mathematical, a lot of it, or certainly can easily be made very mathematical. And likewise, machine learning especially, you're essentially approximating functions, and so being in a language which enables you to treat functions as values like anything else can be super useful there. And oh yeah, as I've said down at the bottom here, parameterized machine learning models are higher order functions, or certainly can be thought of as higher order functions. That is a function which returns another function. So it's gonna, like, if you have a neural network, you can think of that as taking in all of its weights and biases and producing for you a function which takes in its input and gives you an output. And again, being able to, having lots of utilities in your language for manipulating those sorts of things can be super nice. Yeah. So one example I've got here is there's a library called backprop, which does heterogeneous automatic differentiation, which is the full name for backpropagation, apparently. So here I've got a bunch of imports, but basically defining a network thing here, a neural network here, and I've got it's got 2 layers, each with the first layer's got 20 neurons in, and then second layer is 5, and essentially, yeah, we've got this here, and then I've defined this function to run the network with a given input, and the interesting thing here is, oh yeah, and then I have this error thing. This is all fairly standard. The interesting thing here is that the backprop library lets me generate, rather than having to specify the gradient function for this directly, the backprop thing will let me will just make it for me, which is pretty cool. So you only have to define the error, and you never have to define the actual the gradient function yourself, which can definitely save a lot of time. Yeah, so I could do eval BP. What's the order of this? Eval BP. So that's going to. Oh, actually, I don't have any vectors to feed it, so I'm not going to actually run it because I can't be bothered to. But yeah, it works anyway. There are also lots of other libraries. I mean, Haskell is especially used by a lot of academics and stuff, and so a lot of the time, you'll find a library for a new idea. A new mathematical idea in Haskell before you'll find it in any other language, which is quite interesting. Another example of that is there's this library hlearn, which is quite old now. I don't know whether it's actively maintained anymore. I don't think it is, but that came up with a guys who made that came up with a much more efficient way to do k-fold cross-validation. There was just they exploited the fact that most machine learning systems have certain algebraic properties to create a much faster algorithm for doing k-fold cross-validation, which I don't actually know very much about, but seemed very interesting and very cool. They had some excellent graphs. Yeah, and you can use Jupyter notebooks, as I found out the other day, so that's pretty cool. Yeah, you can there's an iHaskell kernel for the Jupyter notebook thing. Oh my god.
What's Jupyter notebook?
Oh, it's like a Python environment that it's kind of like a literate programming thing. Yeah, where you have like text and you have cells that you can then execute.
Kind of runs things line by line and proves the output.
Yeah.
You can easily share them with other people, which is
Yeah, so you can actually have. Oh wow, this is very.
The music came up.
Oh, where's it put the thing? I'm going to. Wait, I'm just going to put this in the directory where it's got the actual examples and stuff. Oh, demo at the top there. Oh no, that's just images. Notebooks. Yeah. So, yeah. Haskell running in a notebook. What is it doing? Okay. Yeah. So, works like any other Jupyter notebook. But yeah, I thought that was quite cool. So you don't even, and there are plotting things and stuff like that. So you can do all of the stuff more or less that you can do in Python in Jupyter notebooks. So that's, I thought that was quite interesting. So reasons not to use functional programming. We already said about the memory usage. Haskell especially, because of the laziness, has quite a few problems with space leaks. You can accidentally end up with space leaks, which can cause terrible crashes, which definitely isn't good. So there's that. There's lots of abstract concepts with funny names, monads, functors, monoids. That often puts people off, and it can mean it's quite hard to get into, and it's quite a steep learning curve if you're not familiar with the terms from maths. And also, there aren't very many functional programmers. So, like, if you want to hire a lot of people to work on a thing, you probably shouldn't write it in Haskell, because you're going to have to pay them a lot more, and they're going to be much harder to find. Also, compilers can get pretty ridiculous. Like, the GHC, which is the most commonly used Haskell compiler, is like a monstrosity. It is so complicated. So, like, in terms of portability and ease of like bootstrapping a language up on a new system, that's definitely a disadvantage. And also just in terms of I don't know, just it's nice to have a simple compiler. I don't know.
Does it compile to native machine code?
Yeah. Well, it has a bunch of backends, so you can compile to native code. You can compile to WebAssembly, all sorts. Yeah. Well, I think WebAssembly now. I can't remember whether that got merged or not, but yeah.
Is Scheme a functional language?
Scheme is, so it's not a purely functional language, so it's definitely a functional language in that the go-to style of Scheme programming is functional programming. But unlike Haskell, it doesn't force you to. You can mutate state in Scheme, like with set exclamation mark, things like that. There's lots of ways to mutate state in Scheme. So it's not purely functional, but I would call it a functional language, yeah.
So there's literally no way around it?
In Haskell, no, yeah. Any I/O you do, you have to do through the I/O monad, which kind of abstracts away the fact that it's actually mutating state under the covers. Actually, it's not your program that does the mutation of state, it's the runtime, the Haskell runtime.
I guess the advantage of that is you can import a library and trust that it won't crash your program. Because when you're using a language that could be written in any style, it's like you have no idea what's going on in the third-party language.
Yeah, also it lets you do some quite interesting things. Like I was playing around, I basically replaced the I/O monad with one that was sending the stuff to a different machine, and it just transparently works. Like you don't have to modify. You can literally take an application written in Haskell, not modify it, but modify the Haskell runtime and have it send the changes it's going to be making over the network to another machine and have another Haskell runtime on that machine actually doing them. And that can just happen, and your program doesn't need to be changed whatsoever. You just have to change the runtime. So there are other reasons you'd want to do it, as well as safety, because you're essentially like making fewer assumptions.
Is everyone, I guess some people in the room are experts, but I guess quite a few, like myself, are new. Do you have any thoughts on characterizing the main languages in this space, like comparing Lisp to Scheme to Clojure, ML? Do you have any kind of...
Oh, they're all quite different. And kind of have different pros and cons. Scheme especially, I really like Scheme because it's so simple. And I think that's really what Scheme has going for it. Scheme is very kind of, you can write a Scheme interpreter in a couple of days, which is very awesome. Clojure, the cool thing about Clojure is it runs on the JVM, and now also you can compile it to JavaScript. So you can integrate with a lot of pre-existing code. If you have a system written in Java, you can quite easily call functions from Clojure. But then you get the other benefits of Lisp, like very, very powerful macros, and some of the benefits of functional languages, like being able to do higher ordered things. Then ML, ML is kind of like a family of languages. Haskell is kind of an ML in terms of syntax. The other MLs I don't have huge amounts of experience with. OCaml I've used a little bit. That's really cool, especially in terms of there's a cool thing called Mirage OS, which is essentially I don't know if anyone's heard of unikernels, but it's kind of like a library that replaces an operating system. So you write your application in OCaml, and then rather than calling through to the operating system, you have this Mirage OS library that you call to instead, and then that just uses stuff provided by the Zen hypervisor. So then you can just create a self-contained image with no operating system involved and run it directly on the Zen hypervisor, which is pretty awesome. So but that's the only thing I've really used OCaml for. Yeah. Yeah. But yeah, it's a trade-off. You have to, I think with any kind of languages, you kind of have to different languages are good for different things, and it's kind of silly to say you should always use functional programming, or you should always use imperative programming, or fill in your favorite programming paradigm or language here. I think the real benefit of languages like Haskell is, like you were saying at the beginning, it gives you a different way to look at things. So, if all you have is a hammer, everything is a nail, it's another tool that you can add that might, in a situation, give you a better way to look at a problem and save you a lot of time. Yeah.
Do you have to be good enough to learn to use functional programming languages?
I wouldn't expect so. I can't really say because I'm okay at maths. So, but I definitely don't think. I think there is a lot of mathematical stuff in Haskell particularly, but other functional languages not so much. Yeah. Also, though, I think the maths that is in Haskell and other languages isn't especially crazy. It's very intimidating when you get started because there's lots of weird words and weird names and really abstract concepts. But if you just smack your brain against it enough times, then it'll eventually stick.
I think just to answer your question in a different way, just from my own beginner's experience of trying to learn some of these languages. So I think I made my way halfway through the big Haskell book, and I did Prolog ages ago. I think from someone who comes from the traditional background of C, HTML in the old days, although that's kind of declarative, the biggest change for my brain was to try and solve a problem declaratively.
Yeah.
So not so much the fact that it's a functional language, but to take a problem and say, how do I solve this within the constraints that functional languages have? and thinking declaratively. So the best example, I don't know if you're able to put it up or not, is the example you use in that book of, is it quicksort?
Oh yeah, yeah.
It's a classic, because it really illustrates the difference. If you're able, I mean, I don't want to impose on you, but if you're able to,
I'm sure I can. I can. Wait, so.
For me, that was the biggest mental shift. So not necessarily being good at abstract mathematics, but just being able to look at a problem differently. So now I try and write Python more pure.
Wait. So quicksort. Let's see. Quicksort. It's like.
I found that in parasitic languages you're often just you tell the computer exactly how you want to solve the problem, whereas with functional you try and find the building blocks that already exist to arrange in a certain way to solve the problem.
It's an interesting question. Have you looked at any report code and see how can I begin to bring some of the functional changes into it? So let's say I'm with Java, bringing some functional stuff from Java. And you sort of think, well, it's easy when I can tell it how to do it because that's what I'm used to. But when you exactly bring this in, when you're not looking at greenfield stuff, you're looking at some of your old code. I guess you certainly have to refactor it quite a bit. And that refactoring would be good, in its own right. But if you tried, rather than just new stuff, refactoring some of your old stuff to use some of the parallels.
Not me, no.
Yeah, somewhat. I haven't had much opportunity to actually do that and go back over the old stuff. Mine was I spent a couple of years doing closure primarily, and then you have the interop with Java anyway, so you have to do a lot of things like that. But I think it depends on testability, because if you're going to do a huge refactoring and you don't have the tests in place anyway, then you may just decide to redo it all in a functional way. And because sometimes if you've got a different mindset, or it's like if you look at someone else's code and you're thinking, I can try and understand this and then refactor it to how I want it to be, or it's actually going to be faster to do it from scratch. So it's
yeah. Especially if there's no unit test there.
Yeah, massively.
Is it worth saying that actually a lot of conventional languages are actually moving to functional?
Oh yeah. No, indeed.
With our front-end work from sort of conventional JavaScript and jQuery to React in TypeScript, and it is basically a pure functional language.
Yeah, no,
it's
indeed.
UI as a function.
Yeah.
Once you get your head around it, it's absolutely amazing.
It is starting to creep in. Yeah, C# as well has a lot of functional stuff.
Well, one of the big differences though is when you write a functional code in a non-functional language, you fall into a lot of problems with performance and things like that.
Yeah.
Because functional languages are written specifically to, improve the code in a way to make it run quicker. But only in big, like big code base. If you're doing small code base or whatever, it's always going to be pretty quick. But
JavaScript is a functional language actually.
But it's got objects, it's always got objects. Well, if you've got objects, you've got state. And then Python supports objects as well.
Yeah.
So
you can not use the objects.
Yeah.
It forces you to do because you can't ultimately state in your
Yeah.
And also C++ with, in C++ 11 and onwards, you've now got proper lambdas.
Yeah, there are lambdas and everything now.
There's algorithms like map and reduce and sum and all those things that you've got in Haskell.
Yeah, absolutely.
As templates in C++.
Yeah. I think the benefit, kind of similar to what you were saying, is the difference with a non-purely functional language is that you can't count on a function. You have to look inside a function to know whether it's, or most of the time you have to look inside a function to know whether it's mutating state or not. It'd be different if there was some kind of thing that you could attach and be like, this is a pure function. And then the compiler treats that differently, and maybe that is done by some languages. But yeah, in general, I'd say Haskell the compiler can do all sorts of crazy things because it knows that all of the functions are.
Well, you can do it in C++ with const to some extent. If you make a function, you know, a const function, and you know that it's not, it may be reading state, but you know it isn't changing.
Is that true?
You won't get around the const in C++, there's no such thing.
And you can't use the external libraries because you'd have to use libraries that every function had that.
Yeah.
But yeah, like, yeah, in Haskell, you just kind of, if you grab some random library, it's like kind of, yeah, also, when you're, is the difference in reasoning, like you were saying, it goes back to the declarative way of thinking about it. And I think a lot of the time, the declarative way of thinking about things is so different, it kind of requires different language primitives. So like one thing you have in Haskell that isn't in any other language is do notation, which is a thing specifically for dealing with monadic values. And obviously no other language has that, because no other language does, well, not no other language. These days people have copied it from Haskell, but very few, like C++ doesn't have do notation, nor does Java or C++, sorry, or C#. And so some of the things that you can express quite nicely in Haskell, because the language is oriented around it, while you can express them in C++, it becomes very clunky. You'll end up with very hard to read code. And yeah.
Do you have a recommended sort of path for complete beginners to start getting? What tutorials should they look at? What should they try? Just like the first
in fact, I'll go to my next slide, which is my references. This book is How I Learned Haskell. It's a very good book. Yeah. That was kind of how I got started, and then I just I don't know, just once I'd got through that, I kind of yeah, I don't know, that was kind of a good foundation to get started off. Goes through a lot of really cool stuff in there. You write a parser. I definitely recommend that as a good first Haskell book. There's also Learn Your Haskell for Great Good, which is another Haskell book. That's another good one. But yeah.
I'm seeing a lot of, the reason I got into Haskell was because I saw the effects in other languages. Like I saw other languages introducing features. And I was like, oh, what's this? This is interesting. Where does it come from? And it ended up being, it came from Haskell. That seems to be happening all across the board, like Java, C++. Do you see a kind of shift in the industry towards functional programming since CPUs have gone multi-core?
I think so, yeah. I think there is a slight tendency towards it. Yeah. Yeah, just because the writing parallel code in an imperative language is just a pain, and writing it in a functional language is fine. Like, you don't even need to think about it a lot of the time. Like, going back to my example I had, the only where is it? The only reason I had to add this, the only reason I had to change this code was because of the lazy evaluation. And in fact, there are other languages similar to Haskell which don't do lazy evaluation. And in those, this would just be parallel by default. You wouldn't even need to change the code. You just need to tell the compiler, oh, I'm running on an 8-core system now, and it does it. So yeah.
I think the other thing about functional is it's also keeping track of state. I mean, that's why in UI work it's, you know, why React is so good. Because in conventional JavaScript, it's like, you know, have I highlighted this div? Or,
yeah.
You know, which classes have I toggled on this bit or whatever? And in React, it's just the whole thing is regenerated every time from the model, and you're using immutable.js or whatever to hold all the state, so you know that you can't mess with it.
Yeah.
But that's still within a single-threaded environment, so
Yeah. There's also that. Yeah.
you're not using it because of parallelism. You're using it just because you can't get your head around the state otherwise.
Mm.
And Swift's just brought out Swift UI, which is kind of a copy to some extent of declarative UI from React. So it just seems to be a bit of a trend that's coming, you know.
And what about GPU level parallelism? Is that useful for?
Oh yeah, it is. So GPUs are another super interesting. Yeah. There's a language called Futhark, which I've played around with a little bit, which
Catchy.
Yeah, it compiles directly to GPU code, but it's a fairly high level Haskell-like sort of language. Yeah, so the representation of pure functions, they're represented very nicely by matrix operations. So a lot of the time you can generate GPU code that runs very efficiently from purely functional code if the language is designed with that in mind. Not really my area of expertise, but yeah, if you're interested in that, definitely look up Futhark. It's very cool. I've only played around with it a little bit, but it's really nice.
Do the functional paradigms remain useful as you scale up kind of from sort of smaller type algorithms into larger sort of systems? Is the functional paradigm still useful on that sort of scale as well?
I would say it's even more useful because you actually are dealing with you have much more to worry about if you're building a really huge system with imperative code, because there's all of this state you have to keep track of, like you were saying with UI stuff. And I would say the benefit of using functional and not having any of that mutable state kind of scales with the code base, because it's more and more that you don't have to think about, if you know what I mean.
It also distributes.
Yeah, it also is very. Yeah. If you've heard of, have you heard of Erlang?
Only
so Erlang, the language is.
Sorry, I said Aladdin.
Oh no, Erlang. Yeah, Erlang is a very cool language for hugely scalable systems.
Which were MQ.
Yeah.
And what's that? Within that as well?
Yeah. But like.
Functional paradigm.
So Erlang, it's kind of functional. Again, it's not purely functional, but within a process in Erlang, there's no mutable data, and that enables the Erlang's abstract machine to switch contexts incredibly quickly, because it doesn't have to worry about saving values of registers and so on. So a big part of why Erlang can do the things that it does is because of using that more functional kind of style of immutable data. Yeah.
So this is sort of getting to one of the things I wanted to ask quite a bit earlier. When we talk about functional programming, we're always talking about how it's provably correct and things like that. And that all sounds great, but do you have like a personal anecdote where provable correctness was a factor in your development of some practical piece of code?
Oh no, yeah, no. I don't think the provable correctness is that huge a selling point, to be honest. I just think it's very cool.
You got one?
Yeah, the bug that took the longest to find in the company that I work for now, out of any other bug that I know of, ended up being a null pointer exception, basically. And if you have the type system checking whether you're returning a maybe or an optional type, then not just that bug, but a whole other class of bugs never exist. And the problem is that when you're typing functional programming in a language, like type-safe language like that, you never see the bugs, so you don't think you're saving time. But the imperative guy next to you is hitting all those bugs and having to go through manually and figure out where they are. Or maybe never hitting them and they end up in production.
Yeah, the question wasn't really meant for the criticism, it was more just that, like, when we talk about functional language, we're often talking literary generalities. We don't hear a lot of stories from the trenches. And it's those stories that kind of like can sometimes be even more convincing than the theory.
So
Yeah.
a friend of mine, he works, his full-time job is as a Haskell programmer, not a side thing, it's his main reason for employment. And I asked him, why, because you don't often hear about companies employing Haskell programmers, although it's growing in some sectors. And asked him why was your organisation choosing to do this, particularly as it was been doing it for a few years, almost before the kind of parallel kind of hardware. And he said the reason was that they were passing around code that I'd written, and then you were using, then you were building on that, and then you were building on that, and you were much more able to accept somebody else's code and not have to look at the definition.
Yeah.
Because the definition
It's tied to abstraction, yeah.
Exactly. I actually thought that I didn't mention the industry sector because it doesn't really make sense to finance, but his reason was that actually it's much easier to accept code from your fellow programmers, but it's in this kind of. He didn't mention performance as a reason, like parallel performance. So they must be doing something really, really complicated in terms of logic.
Yeah.
To kind of benefit from that aspect.
Yeah, the super expressive type systems of like Haskell and similar languages is super nice for just handing code around. There's a cool thing called Google, which is like a search engine for Haskell. And with that, you can literally type in, you're like, oh, I want a function that does this. You're like, okay, so it will have this type, and then you can just search that type signature on Google, and you'll find a library that has a function that does that, and that's super awesome.
Can I ask you a data science Haskell question? One of the things that I came across when I looked in Haskell, which was awesome, was being able to, with big data, essentially like pretend like it's small data and load the whole file in, but because it's lazy, you're only loading a line at a time, it's not really loading the whole file, so the code's massively simplified. Have you come across any cool things for parallel processing of data across like multiple, that in the same way gives you like this simplification where you have a bunch of machines and you're parallel processing?
I can't think of any off the top of my head.
Right.
I haven't really done a huge amount with data science in Haskell, to be honest. Mostly, yeah.
But it feels like what you said about you could replace the I/O.
Yeah.
That somebody must have.
You could make a similar thing. I think there is. I did see something about someone made like some kind of monad that wraps Apache Spark. So I guess you could do that kind of thing with that. I don't know.
I know it's kind of like Erlang's territory really in terms of message passing and parallel processing, but I was just wondering if there was kind of something you could jump in and say, oh yeah, this is a good.
Yeah, no, not off the top of my head.
Last question? Okay. It's great that the conversation is kind of going so good, but just to be fair on people who need to get back, we should call close to it. I guess if you hang around for a few more minutes, people can ask a few questions. Thank you very much. That was really, really fantastic. Thank you.
Cheers.